So in this lecture session, I am going to talk about some of the tensor operations which we need to know before we start deriving the governing equations of fluid motion. The first tensor operation of relevance to us is what is called the dot product between two tensors. Actually, there are two types of dot products that one can define if we are dealing with tensors of order more than or equal to 2. If any of the participating tensors has order more than or equal to 2, then we can define the first dot product as T dot n, and we can also define n dot t. And in general, keep in mind that T dot n does not equal n dot t. If either T or n is more than or equal to 2. T dot n as well as n dot t will actually result into another tensor which will have the order as t plus n minus 2. So here I am using this symbol small t to denote the order of the tensor represented by capital T. Similarly, I am using the letter small letter n to denote the order of the tensor uh, denoted by capital N. So I am saying that the resulting tensor, whether it is T dot n or n dot t, will have the order t plus n minus 2. In case t equals n equals 1, then of course T dot n will become n dot t, and we are quite familiar uh, with this kind of tensor operation. So when n and t both are 1, we are dealing with two vectors, and we know that a vector A dotting with vector B, A dot B is indeed equal to B dot A. So in that special case, these two will give the same result, but not in general. And also in that special case, when both the participating tensors are vectors, you can see the validity of this formula that I mentioned here, that the resulting tensor must have an order 1, which is t, small t, another 1, which is coming from small n, 1 plus 1 minus 2 equals 0, which is a scalar. We are familiar with this idea. Now let's take an example with the tensor t having order 2 and another tensor n having order 1, and let's try to see the expression of t dot n first. T dot n can be written, can be expressed in our Cartesian coordinate system in this manner. So first I write t as a double summation Tij Eij, summation going over I and j, and that is being dotted with the other tensor n, which since it is a first order tensor, I am writing that simply as npep, summation going over p. And again, I want to remind you that since we are going to let these two tensors mingle with each other, I mean they will have some operations going on between two of them, I have made sure that I and j are being used here to represent the first tensor. The second tensor, I am using an index which is different from I, which is different from j. Now this tensor t is actually having 9 terms within it, which are being written explicitly here, and then it has to dot with the n tensor, right? Now to actually perform this operation term by term, let's first expand this dot product in the manner that I have written here. So from here I am taking the first part of the tensor t11 e1 e1, letting it dot with the n tensor. Then I take the second one from here t12 e1 e2 dotted with the n tensor. all the way to the last part of T tensor, which is T33E3E3 dotting with NP-EP. So there are 9 such terms. Of course, I have not written all of them here, but I hope it is clear what will come in between these terms if I really have to write. Now, among these 9 terms, let's first focus on the very first one, which is T11 even dotting with the N tensor. Now, I will write the N tensor. I will expand the N tensor also as N1 E1, N2 E2, and N3 E3. And then I am ready to actually apply the dot product, actually perform this operation. Now, how is this operation going to be performed? So the rule is, when I say dot product, I'm defining a new type of product, and the rule of this product is that the closest unit vectors should dot with each other. So here you will see that in this expression here, this E1, where the cursor is, closest to this E1, so they will dot with each other. In this case, both are E1, so I will get E1 dot E1, which will be just unity. When I go to the second term here, the same rule is to be followed. This E1 has to dot with this E2 here. And then in this case, E1 dot E2 will become 0. So this will not survive. Similarly, the third term here will involve a dot product between E1 and E3, and that is also not going to survive. So out of these 3 terms, only one survivor we have, which is T11, E1, and 1. That's what is written here. Similarly, if I go to T12, E1, E2, this dot product, where the cursor is, and if I want to expand that, I get T12, E1, E2 dotting with NP-EP, and that will have potentially, it will have 3 terms which have been written here, N1, E1, N2, E2, and N3, E3. But then again, only one of these 3 terms will survive, and this time the survivor will be the term in between, because that only involves having a dot product between identical tensors. The other 2, you see, the dot product will result into a situation wherein we have E2 dotting with E1 gone, E2 dotting with E3 gone. So only the middle term will survive, and T1 to E1 and 2 we will get. Now, if you keep performing this kind of operation for all the 9 terms here, you will see that each term, like the first 2 I showed, will have only one surviving term, and accordingly we will have in total 9 surviving terms for T dot n, and all of them have been written here. And once you have all of them here, if you pay attention to the way their indices are changing, you can actually recognize a pattern and write this bunch of this sum of 9 terms as in this compact manner using sigma notation. We will have 2 summations, one over I, another over j, and inside that summation I have Ti, j, and j, ei. So this is what T dot n looks like in Cartesian coordinate system. Having derived this expression for T dot n, my interest is now to find an expression for the other dot product possible between n and t, and that is n dot t. N is coming from the left hand side and t is coming from the right hand side, and they dot with each other. Now, when you perform this, you can follow the same set of steps that we had for T dot n, and one can verify that n dot t will also have 9 surviving terms, and the sum of those 9 surviving terms can be again written as in the sigma notation as what I have here, ni, ti, j, ej, with summation going over I and j. You can verify yourself. I have not written all the steps, but if you wish, you can do it yourself. Now I actually want to compare n dot t and t dot n. So for n dot t, I have this expression. For t dot n, I have this expression, and I want to see whether they are equal or not. How do I compare them? Now, the way to compare them is to actually focus on, say, the coefficient of EI in both of them. So note that T dot n is a vector, is a tensor of order 1. Why? How do I recognize that? I recognize that by looking at this expression of T dot n in the Cartesian coordinate system. Clearly, it has only EI there. I mean, the unit vector is appearing on its own. There is no dyad, there is no dyad of third order or higher order. There is just E1 standing alone there, and that tells me that it's got to be a first order tensor. Same as the conclusion here for n dot t. Here also one lone unit vector is standing in this summation form, and that tells me that it is n dot t is also a vector, a tensor of order 1. And also I want to connect these observations with the formula that I gave in the beginning on the previous slide, when I said that when two tensors of order little t, small t, and small n, they dot with each other, the resulting tensor will be of order t plus n minus 2. You can actually verify that in this case that formula is indeed consistent. So here I am having t as 2, n as 1. So 2 plus 1, 3 minus 2. So the order is 1, which is also in line with the expression that I have in Cartesian coordinate system. Same will be the conclusion here for n dot t. 2 plus 1, 1 plus 2 minus 2, that will give you order of the resulting tensor. So now going back to the question, how do I compare n dot t and t dot n and conclude whether they are equal or not? So the way to do is, since both quantities are clearly tensors of order 1, or they are both are vectors, what suffices is to compare the ith component of t dot n with compare the ith component of t dot n with the ith component of n dot t. Yes, the ith component of n dot t. And if the ith component of one tensor is equal to the ith component of the other tensor, then indeed both the vectors or tensors of order 1 must be equal. Now, if I have to find the ith component of say t dot n, what do? I go to this expression and I identify what is standing in front of EI, that is the coefficient of, that is the ith component of the t dot n tensor, right? So that is going to be Tij Nj summed over j only now, from j going from 1 to 3, right? That this is the ith component of t dot n, because it is the coefficient of EI in the full expression. So as I said a little while ago that I have to identify the coefficient of EI in both the expressions, n dot t and t dot n. The coefficient of EI from Tn I have already identified. EI from t dot n I have already identified. How do I identify the coefficient of EI in n dot t? Now in n dot t, the way I derive the expression, Cartesian coordinate system, actually there is no EI. We don't see any EI. We have Ej here. So what is the coefficient of EI? Not obvious in the expression for n dot t. We have Ej, but EI is not visible. But we can change I and j. Why? Because in this expression of n dot j, both I and j are dummy indices. So there is nothing that stops me from changing this j and the other j that is appearing to I. But when I do that, I have to be careful that if I change the existing j's to i's, I already had i's there, which means I will start getting more than 2 i's. So if I want to change all j's to i's, I should change all i's to something else, right? But I will not change it to something altogether else. I will just change all I to j's. So all j's to I, all I to j will just be adequate for me to achieve what I'm trying to achieve, to get ei in my expression. So when you do that, n dot t, which had this expression, which I derived earlier, I'm going to change all I to j and then all j to I, and I get this expression, which has indeed ei sitting there. Once I have ei there, then my quest was to find the coefficient of ei in n dot t, and it is now clear that the coefficient of ei in this expression will be nj tji, what is left here, and the summation over j. That's what I have written here. So by this time, I have the coefficient of ei in n dot t, double star, and I already had the coefficient of ei in t dot n, which was single star. Now you compare single star with double star here, and we can conclude whether they are same or not. So on one side, I have summation nj tij, j going from 1 to 3. Other hand, we have nj tji, summation going from j equals 1 to 3. And clearly, these are different because here t appears with indices ij, whereas here t appears with indices ji. The order is changed. So in general, my conclusion is that n dot t is not equal to t dot n. Okay? Now let's talk about double dot between two tensors, the double dot operation between two tensors. If now for the double dot tensors, for t and n of order small t and small n to be defined, I mean the double dot operation to be defined between these two tensors, we must have t greater than or equal to 2 and n greater than or equal to 2. Both of them should have this much order. At least they should have order 2, each of them. And what you will find that the resulting order will be, resulting tensor will be of order t plus n minus 4. Okay? And this minus 4 actually comes from this idea that if one dot product is there, remember 2 unit vectors are sacrificed, right? It becomes E1 dot E1. So E1 comes, 1 unit vector comes from the left tensor, 1 unit vector comes from the right tensor, and in the case of a single dot product, both of them sacrifice each other to reduce the order of the resulting tensor by 2. Right? That happened with the first order, with the single dot product. Similarly, in double dot product, what will happen? You will have to take dot products successively 2 times, one after another, and during each of those single dot operations, 2 unit vectors will be sacrificed, one from left, one from right, then again one from left and one from right. So in this way, you can count that in total 4 unit vectors coming from both original t and original n will eventually be sacrificed, and that's what leads me to this conclusion that the resulting tensor will be of order t plus n minus 4. And this idea will become more clear as I take an example for illustration. So let me take an example in which I have the first order tensor t of order 2. I have the first tensor t of order 2 and the second tensor of order 2 again, t and n. And t double dot n, I'm going to write this in using Cartesian coordinate system in this way. Again, making sure that no index is allowed to appear more than 2 times, and that is why I took I and j to express the tensor t, and while expressing the tensor n, I can take any 2 indices, but not I and j. You should not take I and j again. Once I has been used, do not use it again. Once j has been used, do not use it again, like before. Next, I'm going to expand the t tensor in t tensor as 9 group of 9 terms, and then the double dot has to happen. Let's focus our attention first on this double dot product, which is going to happen with t11 e1 e1 coming from left, and the entire n tensor coming from the right hand side. Let's see what happens. So T11 even double dotting with the entire n tensor. Now I'm going to expand the entire n tensor also as 9 terms here. And then one by one, T11 even will double dot with each of the 9 parts, each of the 9 terms that are there for the n tensor. And all these have been written explicitly here on my slide. And then we are ready to perform the double dot operation. Now, rule of the double dot product is the same actually what we had for the single dot product, with the only difference that the single dot operation has to be performed 2 times, one after another. And first, the 2 closest unit vectors will dot with each other. Closest means the rightmost of the left tensor will dot with the leftmost unit vector of the right tensor, and then this will be repeated. So I have shown with these double-headed arrows how these operations will be performed. So first even here dots with even, and that gives me 1. And then the even, which now becomes the rightmost on the left tensor, will dot with what has now become the leftmost on the right tensor. And in this case, both dot products will give you unity, and that is why this term will survive. T11, N11 will be a survivor. That is not the story with all other terms. If you examine, for example, if you look at this term, here the first dot operation will be between even and even, which is fine, which does not kill this term, doesn't destroy this term. But then the rightmost, after the first dot product has been performed, the rightmost unit vector of the left tensor will have to dot with the leftmost unit vector of the right tensor. And in this case, they are going to destroy each other because we have even dotting with E2 that will become 0. So overall, this term will have no contribution. This story will be repeated, you can verify, for all other terms, all other 7 terms in this summation. So the only one term that survives is T11 and 11. Other products are 0. So this was the outcome of T11 even double dotting with the n tensor. Now keep in mind that you have to do this for other 8 terms of the T tensor. But then every time you take one term from the T tensor and make it double dot with the full n tensor, you will get only one survivor, just the way you got one survivor here. You can verify that. So eventually, each one of these will give you one survivor, and when you put together all those survivors, you will have 9 number of survivors, which are written here. After getting all these 9 survivors, you can look at the way their indices are changing, and you should be able to write the full expression using sigma notation, in which you will have 2 summations again, and inside the summation you will have Tij Nji. If I ask at this point what is the order of this tensor, the expression of which we have just arrived at, what would be the answer? The answer would depend on how many unit vectors are appearing in this summation, whether it is a first order dyad, second order dyad, or no unit vectors at all. In this case, there is no unit vector, which actually tells me that it is indeed a scalar. And this conclusion is actually in line with the formula that I gave earlier. T plus n minus 4 is the order of the resulting tensor when 2 tensors double dot with each other. Recall, I started with the T tensor having order 2, n tensor having order 2. So the resulting tensor must be of order 2 plus 2 minus 4, which is 0. In other words, we have a scalar. So this expression and that formula are indeed consistent with each other. Now let's talk about what is called the transpose of a second order tensor M. The symbol that we use for transpose is M with the superscript T. And if M is written, if I'm using Cartesian coordinate system to express the M tensor, then M will be written as Mij Ei Ej. We have seen this in the previous video with double summation. So the transpose of M will be, to get transpose, or the way a transpose is defined is, you change the order in which the indices of M are appearing and leave the order in which the dyads are appearing. That will become the transpose of M tensor. Okay? MJI, EI, EJ represents with double summation, of course, represents the M tensor. There is another way to represent the M tensor. You do not interfere with the order in which the indices of M are appearing. Alternatively, you change the order in which the unit vectors of the dyad are appearing. So you make it Mij, Ej, Ei. That also represents M tensor, M transpose. In fact, these two are the same. In general, M and Mt are two different tensors. However, for some tensors, M equals Mt. Transpose and the original tensor are the same. If that is the case, then M is called a symmetric tensor. It is a special type of second order tensor. For symmetric tensors, it will turn out that Mij equals Mji, where I and j can take value 1, 2, or 3. So, it means that M12 will be equal to M21, M23 will be equal to M32, and M13 will be equal to M31. Some second order tensors are called antisymmetric if Mij equals minus Mji. So even though I am writing this condition as a single equation, mind you, this actually represents six equations, 6 scalar equations. Why? Because I can take value 1, 2, 3, j can take value 1, 2, 3. So the condition for a symmetric second order tensor to be antisymmetric is M12 must be equal to minus M21, M13 should equal minus M31, M23 equals minus M32, and M11, M22, and M33 are all 0. So M11, M22, and M33 all being 0 actually follows from the same condition, because this will imply M11 equals minus M11, which is equivalent to saying M11 is 0. Similarly, for M22 being minus M22 and M33 being equal to minus M33 will result into the two tensors, the components M22 and M33 being individually 0. So this is an antisymmetric tensor. If M is a tensor with its scalar components following this set of conditions, we call that tensor an antisymmetric tensor. It turns out that given any tensor of order 2, actually, you can always split that into a symmetric and an antisymmetric tensor. So a tensor of order 2 can be written as a sum of a symmetric tensor and an antisymmetric tensor. And this definition of the symmetric tensor is A plus A transpose by 2, and that of the antisymmetric tensor is A minus A transpose by 2. Okay. The next type of a tensor operation is cross product between two vectors, which I'm sure everybody is familiar with. The point to keep in mind is that even though we are talking about tensors in general of order, any order, cross product, this particular operation is valid only when both the participating tensors are of order 1. Okay, cross product is defined only for two vectors. So if you take A cross B and then use these relationships, that E1 cross E2 takes you to E3, E2 cross E3 takes you to E1, and so on, and the cross product of the cross product between E1 and E1 will be 0, and E2 and E2 will be 0, and so on. Use all these properties, you can arrive at this expression for the cross product between two vectors, with the coefficients of E1, E2, and E3 being what is being shown here. And clearly, the cross product between two vectors results into another vector. So the order of the tensor remains the same as